Okay, welcome everybody. Let me share the slides with you. No, let's see. I don't want the annotations on again, so let's redo this. Okay, so today we're going to talk about how you can figure out where your CPU time is going, and that is the first step in making your programs, well, a key step in making your programs faster. So, what do you know so far in terms of making your programs faster? Well, you know big O analysis. You know that an order n squared function for large n is going to take longer than an order n log n one. And you can analyze, given the techniques you learned in ECE 244 and the fact that the C++ standard library tells you the complexity for most of its functions, you can analyze, for this data structure and this set of loops, what's the big O complexity. And you can go look for large big O complexities and change them to better loop structures or better data structures. So that's a useful technique. You can also guess based on some of the knowledge you gained in ECE 244. So in ECE 244, you learned that the copy constructor can be slow if you're moving around big data. And instead, you can do things like pass by reference, where you don't actually copy a large amount of data. So you can inspect your code, and you can often find bottlenecks like this. So you should probably start with big O analysis, make sure it's good. If it is good, look for large constructor calls. That's a useful thing to do. After that, you might start guessing based on what you think you know. So you're just looking at the code and you're guessing this might be slow and that might be slow. This is common, but it is problematic. People aren't that good at guessing where the time goes in a large program. A large program, it's hard to keep a track of everything that's going on. And on top of that, modern CPUs are very complicated. And exactly what's fast and what's slow and how much of your time is going to getting stuff from memory versus doing computation is also very hard to predict. So this is not ideal, but people do it all the time. And you can use the stopwatch app on your phone to time things that take a long time. So you could time slow events in your program using that, but you can't time things that are very fast. Okay, so those are all useful, but they're not enough in general for us to figure out how to make a program faster. And this is a classic quote from Lord Kelvin, if you cannot measure it, you cannot improve it. So how can we measure more about where our program's time is going so we can improve it more? I'm going to go over three different techniques. So the first one is manual measurements, where we write code to measure time. The advantage of this is it's got very low overhead. If you do it correctly, it doesn't impact the runtime of your program much. So there's a problem sometimes when you're measuring if you might disturb the thing you're measuring. But manual measurements don't disturb it very much. You write a little bit of code, it doesn't slow your program down much, and you get pretty accurate answers. You can use this to measure even parts of a function, whereas the other techniques I'm going to show you generally you can't really figure out what parts of a function are slow. You can only really figure out which functions are potentially slow. Disadvantage of this is that you actually have to write code. So if you don't know where to start and you've got a big program, it might take you quite a while to write all this code. So other techniques you can use are you can sample using the debugger. And again, I'll demo this in a little while. The debugger has buttons called pause and continue. So you can actually stop your program, look at where it is, and then hit continue to keep going, stop it again. So you can coarsely sample where the runtime is spent by just interrupting multiple times and seeing where are you. Now you can only do that at a pretty slow rate. Maybe you can click those buttons once a second, maybe twice a second, but not very often. If you want to sample your program more often, you can use a profiler to do essentially the same thing. This profiler is basically automating this pause and continue procedure. The profiler interrupts your program, and in ECE 243, I assume you've studied interrupts now. So if you have or haven't, let me know in the chat. It's not essential that you do, but what I'm saying makes more sense if you have. So have you guys studied interrupts so far? Not yet. Okay. Well, I guess their name is pretty descriptive. Interrupt basically stops the processor from doing whatever it's currently doing and says, go do this other thing instead, and then come back to your work. So a profiler interrupts your program at some sampling rate, common ones are 100 to 1,000 times a second. And every time it interrupts your program, it basically records where are you, what function are you in, and how did you get to that function. It looks at the call stack. It records some information, and then it resumes execution. So lets your program go back to doing what it was doing before. But it's interrupting it, maybe once every millisecond. So it's building up a picture that's more detailed than you could do by hand of how often are you in various functions and how did you get there. So this is a good way to identify bottlenecks. Okay, so let's start with the first technique, measuring performance manually. So we're going to write some code to figure out the CPU time of various functions. So the way you do this is it's always the same technique. You get the timestamp before the region of interest, before the code you're trying to time. Okay, whoops. Then you get the timestamp after the code that you're interested in. You subtract them to get the difference, and then you output that in, say, seconds. Okay, so let's look at what that looks like in code. So let's say I'm worried about the performance of my act on button press routine. And I'll fix this afterwards. This is not quite the right function prototype, so don't be confused by that. So the act on button press, remember, if a user clicks the mouse, this function gets called. And we were using it last tutorial to figure out what intersection they wanted us to highlight. And we did a little bit of computation in this. We computed the longitude, we computed the latitude, and then we took that latitude and longitude and we called our find closest intersection function. And our find closest intersection function was order n. We actually looked through, or at least in my solution, it's order n. I looked through all of the intersections, seeing which one is closest. So that makes me a little nervous. Maybe that's slow. So I'd like to time it. Okay, so how do I do that? So first thing I need to do is get the timestamp before the region of interest. Well, the region of interest is my whole function. So everything that I'm doing in here, I want to know how long it takes. How do I get that timestamp? Well, there's a chrono library, chrono header that is a part of the C++ standard library that has all of its time-based functions in it. So I include that, and then I'm going to call a function called now. Okay, now is inside the standard library, inside the chrono namespace, inside this class. So it's got a long name, but it basically just gets the current time. And I'm going to store that in an object, and I'm going to call that object start. And I don't really care what its type is. I'll just say auto. It's some chrono type, and the compiler will figure out what it is. Okay, now I need to get the timestamp after my code. So I just call the exact same function again. So call now again, and I'm going to get that time in a new object that I'll call end. Calculate the difference. So I just take end minus start. That's the time. I don't know what to do with these chrono objects. So chrono provides some casts. So this is a cast operation. Again, it looks kind of funky. Don't worry about it. This is the code you need. It converts this object, which is the difference between these two times, into a time duration in seconds. So that's all that did. It gave me another object called delta time, which is now the time difference in seconds. And I want to print that out. And the way I print that out is I'll take my delta time, and it's got a member function called count, and that's going to print my time in seconds. It'll be in seconds because I asked for it to be in seconds here. And I'm going to print out, okay, act on button press took, and I print out this time. So it's not a lot of code in order for me to time this function. Now I might want to save this to a file, because if I'm going to do this for a lot of functions that might be called several times, it could get a bit messy. If I print it to the screen, it might be interleaved with other messages, so it could be hard for me to interpret. So I'm going to save this to a file. So what am I going to do? It's actually a comment I'm going to fix afterwards. It's a bit out of date. I'm going to open a file, and the file I'm going to call actonbuttonpress.csv. So CSV just stands for comma separated value. So because that's the format I'm going to use. So I'm going to write this out in a very simple format where I just write values, so strings or numbers separated by a comma, so that it's easy for me to open in a spreadsheet like Excel. So that's the name of the function. And I'm going to create an object of type output file stream. So I'm creating an object kind of like cout. It's a stream and it's for output, but instead of going to the screen, it's going to go to a file. Which file? This is the name of the file. Okay, I need to give that object a name. So, and actually this name is wrong. So it should be profile CSV file, because that's what the rest of the code assumes. So what this line of code has done is it basically is a constructor for an output file stream. You give it the name of the file and it'll open that file. And now I can access that output file stream just like it was, just like cout. So this is kind of like cout, all right? But it's actually a file on disk. But I can write to it using the same operators that I would use for cout. So it isn't cout, but I use it using the same interface as cout. Okay, so, and I'm going to write, I want to use this file to capture information on how fast or slow act on button press is. Okay, so here's my act on button press routine. And what I'm going to do is I'm going to get my start time by calling now. And I could compute the end time and print it to a file all down here at the end of the routine. Well, that is what I'm going to do. But to make that a bit cleaner, I've written a helper function. Okay, so this helper function, I'm going to pass in the start time, and I'm going to pass in the name of my function, all right, like a string to identify who am I. And now let's go look at that helper function. So that, let me draw this in a different color. That helper function is up here. Okay, I called it profile CSV. And what does it do? It basically just gets the current time. That's my end time because I put it at the end here. I calculate the elapsed time by subtracting the end time minus start time. And then I print out to this profile CSV file whatever string was passed in. So I passed in a function name. I'm going to print that out. And I'm going to print out what the elapsed time is. So every time act on button press gets called, one new line will be added to this CSV file. And the reason I've written this helper function is to basically make it really easy for me to time functions. I only need 2 lines in the function. I need to get the start time at the beginning, and I need to call this helper function at the end. The helper function will get the end time, work out the difference, write it out to the file. Okay, so does it make sense? So you try to use helper functions as much as you can. One last thing I've done here is we have this if-def profiling and end-if. So do people know what those are for? Have you seen if-defs and end-ifs in your code so far? Yes, for macros. Yeah. So these are what are called preprocessor directives. In C++, this basically gives some instructions to the compiler. Somewhere in my code, if I actually want this code to be compiled in, then somewhere I actually have to do this. I have to say define somewhere before this. So normally at the top of this file or in some header file that everybody includes, I would write define profiling. As long as I've defined profiling, then the compiler will include these lines. If I comment that line out or it's missing, then the compiler will not put these lines in. It just disappears from my code. Okay, why is that useful for this kind of code? This is like extra code that's generating extra output from your program that is useful to a developer. It's not really useful to an end user, so you might want to turn it off before it goes to an end user or before you submit to your TA. And this, you don't have to, but it might be something you want to do. This allows you to do it really easily. You can uncomment or comment this line and turn off for the whole program, because I might be timing all sorts of functions. I can turn all this output off right away. Okay, so this is a good way to do it. And yeah, basically we're writing this in comma separated value format. So you see there are commas between all of the function name and the elapsed time, so that we can load it into a spreadsheet easily. Yeah, so the question of functionally, does this, this if-def and end-if, is it the same as commenting out this block of code? Yeah, it's exactly the same as if you just went in and commented it all out or deleted it. It's just more convenient. If there are only 3 lines of it, it's only a little more convenient, but the idea is you might have, if you have more code related to profiling in your program, all of that code can be taken out with just this one line. Okay, so it's more convenient. Let's see. Okay, and I might want to see this as the program's running. So basically, by saying end line instead of end L, this actually makes sure that the data goes out to the file right away. And otherwise, it could be buffered. It might not go out right away. If I want to look at the data that's being generated to this file as the program's running, this is kind of convenient, but you don't have to do it. Okay, so this produces an output file. If I did this for all sorts of functions, which is what I'm going to do next, that basically has function names and how long you spent in that function. And every time the function is called, you get another row. So any questions on that? So there are no questions. I'm going to go quickly show you a demo of this. Okay, so this is, let me bring this back up. This is actually the golden solution that, like a reference solution that we've written for the course. And let me go show you some of the code for this. So the key function, whoops. Okay, so I'm actually not going to time the act on button press routine because that routine doesn't get called that often. It's only called when the user clicks the mouse. People can't click the mouse that often, so it's probably going to be fine. So instead, I'm going to time various functions in our screen redrawing routine because that matters more. We get that gets called a lot. So this is the main screen redrawing routine for our reference solution. And we've basically added in this instrumentation that I talked about. So we call at the start of it, what is the current time, and store that in start time. And at the end of the function, let me just skip through this really quickly. At the end of the function, we call this profile CSV helper function. And we say the time for the whole draw routine, well, figure it out and write it to a file. So let's go look at this helper function. Okay, this helper function is basically the same as what I just showed you on the slides. It takes a starting time, takes the name of a function, a string that represents the name of the function. It just works out how much time has passed between now and the starting time, and it prints a line to this file, profile CSV file. Okay. And actually, this is a question that came up in the previous tutorial. Could I move the if-defs inside of this function instead of having them around the function? Because if you go back to where I was, you'll notice here I put the if-defs around the function. And yeah, I could. And that's probably a bit cleaner because then I won't see as many if-defs. So maybe I should move those if-defs inside here to just make this function do nothing, and it'll shorten my code a bit. Either one works. If I go look at this profile CSV file, what is that? So that's the stream I'm writing to. It's a global variable. Okay, so I've made a global variable that is an output file stream. Here, I didn't actually give a file name, which means it is not being opened. So I have to open it somewhere else. And we actually opened it in load map. So if I go look for this and do a find in files, let's see what happens if I do that. Okay, so in my load map, this is another way you can basically open a file. You can explicitly call the .open function. So in our load map, we actually open a file called funcperf.csv, comma separated value, and in our close map, we close this. So that works fine. I also could have just put this name in the constructor for the global variable. So that would have worked too. That's what I showed you in the slides. This is an alternative way to do it. This will also work. You can actually see our load map is also being timed. So I get a start time here at the start of load map. And if I go to the end of it, you'll see that we call this profile CSV file. Okay, so I got a helper function. I'm calling it in load map. I've already opened the file. I've got a global variable to write to it because that's what this function assumes. And what I really want to use this for is to time my screen redraws. So I've got a timer around the whole screen redraw. I don't need this right now, but basically our screen redraw function, I've actually wrapped a loop around it so I can make it draw more than once. That's just to slow it down for demos. But right now it's drawing just once, which is what you would normally have. And hopefully this is how your screen redrawing function works too. Ours basically calls a whole bunch of helper functions. So it calls a function to check, are we at a high zoom level? Because that's going to affect how much we draw on the screen. If I go look at that, in this high zoom level, I get the start time at the very start. And at the very end, I write out to the CSV file how much time it took with that little helper function call. And every one of these helper functions has that. So draw all features. I go look at that. I'm going to show you that code because that's pretty important. It says draw all features code. Basically goes through and draws the lakes, the rivers, the buildings, etc. It takes a Boolean variable telling it whether or not we're zoomed in and it should show extra stuff or not. And it's timed. So it's got a start time here. And we call this profile CSV to write a line out at the end. This draw all segments is drawing the roads. So that's our top routine for drawing the roads. And again, it's timed. So it's got a start time. It's got some logic to figure out, are you a major road or minor and so on, and choose colors. And then it draws all of those roads. And then at the end, it times itself again. So all these routines are timing themselves. What else is there? There's a routine to draw text labels on points of interest. There's a routine to draw street names. There's a routine for milestone 4 to visualize a delivery route, but that's not going to do much right now. And then there's if we've turned on an option, the subways variable, it'll draw the subway stations. And then that's the end. And then we also time the whole routine. Okay, so we've got kind of overlapping timers. We tell them all the helper functions, and we're also timing the total routine. So, okay, I'm going to run this to generate some output of where do we spend our time. What build should I use? What do you think? So NetBeans has multiple build types. What thing should I use? Yeah, so I should use release, right? I don't care how fast the debug build is. I might get confusing results or misleading results because it's not optimized. So I should build and run the release build. So let's do that. I'll do a clean and build because I just changed the configuration. Okay, so it's done. So now I'm going to run it. Okay, so I'm trying to time my redrawing routines. So I basically want to run them a few times to generate more data in this spreadsheet. And I'd kind of like them to run with all their features on. So I'm going to turn street naming on. I'm going to turn the subways on. And now I'm going to start zooming in. So I've got some redraws that are going to be pretty zoomed out. And each time I zoom in, okay, that redraw is probably going to be a bit different. You saw a bunch more features got drawn. So more detail got drawn. Now I'm going to just pan around a bit to generate a few more redraws. And that's probably enough. Okay, so I hit the proceed button to end it. Okay, so there is an office tool, well, a free office tool called LibreOffice. And LibreOffice Calc is basically like Excel. So this is the Linux free version of Excel. And I'm going to open using that spreadsheet program. So I could do this in Excel, but this one's on the UG machine, so it's more convenient. I need to go look for that CSV file, and I called it funcperf.csv. So I'm going to open that file. Okay, and there's the file, and it's pretty simple. So let me go to the top of it. So it's just function name and then time in seconds that function took when it was called. So load map takes about 7 seconds, but that's not what I'm concerned about right now. I want to look at my drawing functions. So this is my very first screen redraw. And the first things I see are all the helper functions because they finish before the overall function. So this is my first redraw. I see a bunch of helper function calls, and then I see, and then I see the time for the whole routine draw. Okay, so the whole draw routine took about 0.28 seconds, and most of that was drawing features. That was 0.27 seconds to draw the features, about 0.01 to draw the roads. You notice in the graphics, when we're zoomed out, we're not actually labeling the POIs and we're not labeling the streets, so those didn't take any time at all. This is a bit slow, okay? So a redraw that takes 0.28 seconds means we're only going to get 2.5 direct redraws a second, which isn't great for scrolling and zooming. But the next redraw is actually considerably better. So draw all features drops down to 0.04 seconds. The roads are about the same, 0.01. All the labeling functions aren't doing anything yet. Traveling salesman's not doing anything yet. And the whole redrawing time was about a 20th of a second. So a lot better. This happens sometimes. So the very first call to our drawing routine was slower than the other ones. And I don't 100% know why that is, but there are lots of reasons that it could be. You probably haven't learned much about, have you learned about processor caches yet? So type it in the chat if you've heard or have not heard of what a processor cache is. Yeah, so you will later. So basically memory is slow. Okay, so processors keep recently used memory items on chip in something called a cache. So the very first time you access some data, some new and large data, it can be slower because you have to go off chip for all of it. And then after that, it can get faster. So that's a likely reason why draw all features got faster. It's also possible if I dig down into the underlying code that we've written there that we have some code that does something different the first time, sets something up. So, but I don't care too much because my first redraw was slower. But if you look, all of these other ones are faster and are now more consistent. So this next redraw is again about 0.04 seconds for draw features, 0.01 for draw the roads, and about 0.05 overall. And that's pretty consistent for the next while. So I don't really care much about the first one because one redraw being slow is not my biggest problem. As I'm going through this, we're getting higher and higher zoom levels. So let's just go down and see what happens as we go to higher zoom levels. And let's go maybe towards the end because the end is like where I know I'm zoomed in a lot. So here's my last redraw where I'm zoomed in a lot. And draw all features got a lot slower again. So it went to 0.29 seconds. Draw all segments has slowed down some too because we're drawing more streets. So it takes 0.04. Labeling the POIs, we're now starting to draw some text. So labeling the POIs took 0.03. Labeling the streets took 0.03. Drawing the subway stations is still really fast, so less than a millisecond. And the overall draw was a bit slow, 0.4 seconds, which again means like 2.5 redraws a second. Okay, so what does this tell me? I shouldn't worry about the labeling routines, like text, the drawing the street names, drawing the POI labels, which are their names. That is not a major problem for me. Okay, I've got bigger fish to fry, so I should not bother with that. Let's see what happened here. I think I lost my VNC, so I might have to go and restart that. So bear with me for a moment. Let's see if this is alive. Okay, so Tim Trant just killed my VNC session. Okay, let's see. So let me restart this. Okay, so let me bring that back up because now I'm going to have to go reload NetBeans. I think I've had that session running for 2 days, so he's got a timeout of after a certain amount of time they get killed. Okay, so it's a test of how fast I can get back to where I was. Okay. Yeah, so the question is draw redrawing the map? Yeah, it is redrawing the map. And Truman, you're right. For the first redraw, I likely have some setup code. I haven't actually gone and looked closely enough recently to know exactly what's going on there. But you're right that that's likely a factor as well. I could try optimizing that, but I just don't care, right? I want to focus on my repeated redraw functions. So, and let me make sure I open the right one. Yeah, it looks fine. Okay. Yes. So the question of does draw refresh the map? That is the kind of root of our screen. That's like our draw main canvas function. So it does all of our redrawing. And I guess we just talked about this, so maybe there's not much more to say. So what I've learned from doing this is that I need to make draw all features faster if I want my screen redrawing to speed up, particularly when I'm zoomed in and when it's drawing all the buildings. I also spend some noticeable time drawing roads, and everything else is pretty negligible. I shouldn't worry about drawing how long it takes to draw the street names and so on. Those are not big problems for me. I shouldn't worry about subways. So I learned something pretty important here. If I actually just said it's not fast enough and divided up a bunch of tasks across my teammates, we might have wasted a lot of time optimizing things that don't matter. Okay, so let me go back and share the other screen now. Okay, so let me get my view back to a more reasonable view. So hopefully that demo was useful. So it doesn't take a ton of code to time your UI, but you do have to write some code. So you have to have some idea of what code to measure, and sometimes you might not have much idea of where to start. In a large program, it might take quite a while to just put timers all over the place if you don't know where to start. So what can we do if we don't know where to start and we don't want to just start writing timers? Well, we can run the debugger and do something called manual random sampling. Let me change the text, the color of this. So we run the debugger and we can stop it using this button. That's the pause button. Once you stop it, you can click on the call stack button to see where am I. Okay, so here I'm deep in some standard library. I don't care about that much, but I can see I came through pushback, and pushback was called by draw segment. Okay, so my draw function called draw segment, which called pushback. And then I don't really care about all the details of what the standard library does to implement pushback, but this gave me some information. Once I've seen how I got there, what I'm doing, like what function am I in, how did I get here, I can hit this button, the continue button, to have the program continue running. And I can do this multiple times. So I repeat this and I keep some notes on, well, where am I? And I see, do I tend to wind up in the same function over and over again? You can even see what loop am I in, like what line am I in inside that function. So that can tell you that's where I need to go optimize. Sometimes it's just that obvious. Every time you pause and continue, you just wind up in the same spot. And that means that's my problem. I don't need to look any further. Okay, so let me quickly demo that. Okay, let's see. I've got NetBeans going. Okay, so what I want to actually sample, what I want to figure out is where am I spending my time when I'm redrawing? That can actually be tricky because the redrawing doesn't take that long. Even my slow redraws are still 0.4 of a second, which is going to be probably faster than I can click pause and continue. So I'm actually going to slow them down. The way I'm going to slow them down is I put a loop around my redrawing function. And so now I've just changed the number of times it redraws to 30, which is not useful. I would not want to submit this, but I'm slowing down my redrawing on purpose by a factor of 30 so that I can do this pause and continue trick and see where's the time going. If the function was already really slow to begin with, I wouldn't have to do this. But for these screen redrawings, they're fast enough. I can't really tell otherwise. Okay, so I'm going to compile release again because I want to test the release build. That's what I really need to be fast. Before I was running, just pressing this green arrow, just run it normally. Now I'm going to press the debug button. I actually want to run it through the debugger. Now, normally you don't run the release build through the debugger because it's easier to understand the debug build. In this case, I don't really need to understand the details of what's going on because I'm not really trying to debug it. I'm just trying to see where do I spend my time. So I can run the release build through the debugger in this case, and it's a useful thing to do. Okay, so I'm going to start zooming in so that I can just watch. Basically, I'm going to hit this pause button as the redraw is in progress and try to see where do we spend our time. So let's turn on names. Let's turn on subways so we have everything going. And let me zoom in a bit here. And my redraws are going to be slow because I've intentionally slowed them down. I still didn't catch it. Okay, I clicked on pause, and I'm in this poll routine, which is called by application.run. This basically means it's just waiting for input. So I need to continue. I missed it. It's not doing anything useful for me right now. So I'm going to zoom in a bit more because I think I need to get to the spot where it slows down. Even with the factor of 30 slowdown, it's hard for me to see what's going on. Whoops. Okay, so I just want to keep that going. Okay, so now it's slowing down because I'm zoomed in a lot. So I just clicked on pause, and where am I? The call stack is active. So I can see I'm in draw feature, and I'm actually on this line. Okay, so I'm in this line of draw feature. How did I get there? I got there from draw all features, which was called by draw. Okay, that makes sense. My timing number said this routine was kind of a problem. Let's go again. Okay, and then I hit pause again. Where am I? I'm again in draw feature, and draw feature called draw line. So I'm actually in draw line, but draw line was called by draw feature, which was called by draw all features. Okay, so I'm drawing a line. I'm gonna keep going, pause again. I'm again in draw line called by draw feature. If you look down here. Okay, now I'm in I'm in a routine that's inside of EasyGL, but that routine is called by fill poly, and fill poly was called by draw feature. Okay, so so far I've been hitting everything is drawing calls from draw feature. Some of them are lines, some of them are polygons. Okay, hit that again, hit pause. I'm in draw feature and I'm drawing a line. Well, I'm actually inside EasyGL, but if I look back of how did I get there, it was draw line, which was called by draw feature. Let's do this a couple more times. Okay, draw feature again, filling a polygon. Okay, now I'm back to polling. So the redraw is done. And if I go look here, the UI is going to be active again. Okay, so just from this course sampling, I found some information out. This information is not super surprising because I already kind of knew it from the timers that I inserted in the code. Draw feature was my big problem. That's where I kept hitting, when I hit pause, that's where I kept winding up. I got a little bit of new information. I was sometimes in draw line and sometimes in fill poly. So that tells me that it seems likely that both the closed features, so lakes and parks where it's a polygon, and open features, so shorelines and rivers where it's a line, both of those seem to be taking significant time. Without having done this pause and continue, I might actually think that it was only the big polygons that would take a long time. But it turns out that I'm spending quite a bit of time in both lines and polygons for features. Okay, so I'm now going to just hit the proceed button to end the program because I'm kind of done with that. So, any questions on that? There's actually a really useful technique, by the way, too, if your program hangs. If you've got an infinite loop, you just do this pause and you'll immediately find where's my infinite loop because you'll be right in it. Okay, so the last technique I'm going to show you is automatic profiling. So automatic profiling, or measuring performance of the profiler, is basically just a faster version of what we did by hand. So you compile with the profile configuration. So in NetBeans, we have different configurations. You actually select this profile one, or if you like the command line, you just make with configuration profile. Then when you run the exerciser, so we can run a test case, I'm going to run the Toronto test case. You specify an extra option, -- profile. And that's going to produce some data in a big file called perf.data. And then we're going to run a tool that we wrote for this course called EC297 Profile Visualize will let us see what's inside that file. Okay, so 3 steps. Build with profiling. Building with profiling basically tells the compiler to insert some extra code so that we're going to interrupt the program often and see where it is. And then we run the program with some input that we're interested in and this profile option. And then we visualize the data that comes out with this EC297 Profile Visualize. Okay, so I'm going to run this for you in a minute, but let's just take a look at what comes out. So this is, if I run this command to visualize the data, so EC297 Profile Visualize, it builds a visual representation of what's called the call graph. So nodes in this, the boxes, are functions, and the edges are calling relations. So this edge means that this function called this function. And the colors help you see the time spent, but more importantly, there are numbers written on these boxes that you can see when you zoom in. So I'll zoom in a little more. This box says we're in program draw Toronto, because that's actually the name of the unit test. And we're in function draw. That's our screen redrawing function. And function draw doesn't take much time in its own code. It takes 0% of our runtime. But if we include the functions that it calls, all its helper functions, it actually takes 74%. So this is a pretty important routine then. 74% of our runtime in this run went to it. How does that break down? Well, this edge has got 58% on it. That means the function that we called at the end of this edge took 58% of our total runtime when it was called from the draw function. Okay, what is that? It's draw all features. So we already saw that that's an important function. In this particular profile run, it took 58% of our time. Not in its own code. So in the code in that routine, it was only 0.7%. Most of this time is in its helper functions. So what helper functions did it call? It called draw feature, and that took 37% of the total runtime, including the functions it called. Get feature type, so figuring out if you're open or closed, took about 17%. So that's actually pretty significant. If we look at what else did this draw function call, it also spent 15% of the total program runtime in draw all segments. So drawing the streets. So drawing the streets, somewhat important. Drawing all the features, so the lakes, the buildings, etc., even more important. And where did the time go? Well, you can dive down deeper and deeper to see where the time went. Okay, and this just tells you the things I just said. There's another way you can build this visualization. So if you use that same tool, profile visualize on the same data, but you specify this option, -t or type flame graph, it produces a different visual representation of the same data. And for this representation, what it doesn't draw boxes of functions calling each other, it draws bars. The width of a bar is proportional to the time spent. So let me change my color here to green. So the unit test takes all the time. Okay, so draw Toronto is everything. Draw Toronto calls redrawing through a few different ways. So translate is what happens when you actually move the like pan the picture. Zoom in is when I'm zooming in. Both of those call redraw. Okay, so they call the redraw function, which calls draw. And same thing over here. So everybody's calling draw. There are a few different ways to call it, but in the end, they all call draw. So let's zoom in on draw. Okay, so if I double click on draw, I'll zoom in on it. And where does its time go? Well, most of the width above it is draw all features. So it means it calls draw all features, and that's what takes most of the time. It also calls draw all segments, and that takes some time. Nobody else really mattered. It calls a few other functions, but they didn't matter. Draw all features is basically just a loop that draws every feature one by one. So almost all of its time goes into draw feature, that helper function. And that time breaks down into a few pieces. Figuring out if it's a closed feature, drawing polygons for the closed ones, and drawing lines for the not closed ones. And this says that the lines, so the rivers and shorelines, actually take a little longer than the parks and oceans and so on. So any optimization, has to include them. Okay, so that is what that flame graph looks like. Let me quickly do a final demo. Okay, and the first thing I'm going to do, I have actually a nice profiling run that I'm just going to save. Let's see. So I already have data from a long run that I did where I clicked on lots of stuff to get lots of good data. So I'm going to save that. Just going to copy the data because I may not click on things for as long here, which means I may not get data that's quite as comprehensive. Okay, so when I'm going to do this kind of profiling, I want to build the profile configuration. So I just switched to it and I click clean and build. It leaves most optimization on, which is good. It turns one optimization off called function inlining. Function inlining can paste the body of one small function into the calling function. That can speed your code up by getting rid of the actual function call, which has some overhead. But it makes it harder to interpret the profiling results because some of your functions just disappear. So when I turn on this profile option, that optimization is turned off. So your program can run a bit slower. And also we basically have added in additional code to do the interrupting of your program and gathering where are you. Okay, so now I need to run this. So I just run it normally. Let's see. Actually, I'm going to stop this because I probably shouldn't run it this way. I should run it from the command line. Okay, so let me go out and, because I need to specify the dash profile option, and I'm not quite sure how to do that. I haven't set up I need to go check that the profiling setup in NetBeans is going to do that. So because I don't want to risk that, I'm just going to do it from the command line. So it's EC97 exercise. I'm doing milestone 2. I don't want to run all the tests. It's going to take too long. Run tester, draw Toronto, and I want to send in that extra profile option. Okay, so now it's running, and as it's running, it's being interrupted and it's generating data about where am I. And that's all going into that perf.data file. Okay, my redraw is kind of slow because I've still got that code active that does 30 redraws. So let's see, I'm going to turn on subways. I'm going to turn on text names so that I get the most information I can. And I'm going to zoom in a bit so I get to trigger a few redraws. Okay, so I basically, just zooming in, letting the redraws happen. Again, they're slow because I'm really doing 30 of them at a time. And to get good profiling data, I should do this for a little while. make sure I really exercise the user interface. I'm going to not do any more of this just for time reasons. So I'll hit proceed. And now I'm going to visualize the data. So this just generated a perf.data file. Now I'm not going to use that one because I ran the UI for longer before. So I know that that data is good. So I'm going to do a data file that I already generated from running the UI for a while called perf.data2. And I'll publish a quick start guide shortly on this, but basically we're using this EC297 profile visualize tool. And we just tell it that the data I want you to visualize is perf data 2, which I generated before. If I wanted to use the run I just did, I'd use perf.data. Okay, this data file can be big. So this takes, maybe it takes, I think this one will take me 30 seconds or so to load, and then we can take a quick look at it. Okay, so there it is. Okay, so I can use Shift plus to zoom in, and I can grab the screen to just pan around. So over here, you can see this is Draw Toronto. That's the name of the unit test. That's the whole program. And this says, this is basically not my screen redrawing. This basically says I spend about 5% of my time in load map and 1% of my time in close map. So if I was trying to optimize those, I could go down and look at, where did that time go? But I don't care. I want to optimize my screen redrawing. So I'm going to go over here. So the name of the test is Draw to Toronto. That's the program. Draw map is the redrawing, the main bring up the window routine. And that takes 76 or 78% of my times in draw map. If I trace down through that a bit, I'll see that where that really comes from is this EasyGL canvas event, which is basically a redrawing function that's calling eventually my draw function. Okay. So my draw function is taking 93% of the total CPU time. So that's my hotspot. That's what I care about. So now that I figured out, okay, this is the key routine, I can look at where does its time go. It takes 93% of the runtime. 75% of the total runtime of the program came from this routine that is called by draw. So draw all features, which we've seen before. And where does its time come from? Well, spend some time in get feature type, 4%, sometime 5% in get feature points, 18% in fill poly, 10% actually checking if it's a closed feature or not. So that seems kind of wasteful. And 35% in draw line. So this tells me, a lot of information about how I might optimize this. I have to draw fewer polygons and fewer lines. That's the number one thing. Maybe this is closed feature can be sped up because that seems kind of high too for what it does. If you look at this, you can also see that draw segments takes 15% of my total time. So drawing the roads takes some time, but it's not as big a deal. And it kind of spends its time in a more diverse set of helper functions. It's actually doing some manipulation of vectors. So I might want to look at that. Why is it actually sticking things in vectors? Maybe I can get rid of that and pre-compute more. So it looks like there might be some room for optimization here, but it's not the number one place to go. I got to basically draw less polygons and less lines in order to speed this up a bunch. Okay, if I want to, so the last thing I'll show you is what does this look like if I just use that other option? So same command, but I basically specify this -t Flamegraph option. It's just going to visualize the data in a different way. So again, this will take a minute to process, and then it pops up. So the test is Draw Toronto. That's all the time. But basically, all of these big bars are different ways we can get to the redrawing function. So let's just pick this one. So I double clicked on it to zoom in, and we can see we spend most of our time for a redraw and draw all features, and some in draw segments, And then when we look at, well, where does draw features go? It spends some time in drawing lines, a bit less time in drawing polygons, and some time in getting the feature type. So same information is presented in a different way. And then you kind of get down to the details of what's being called by these. But what I can really optimize is how many lines I draw, how many polygons I draw, and maybe this get feature type I can make faster. These ones are now down inside EasyGL, so I'm not going to go rewrite that. I'm going to work on the how many lines am I drawing. That's probably the first thing I would do here. Do I really need to draw all those, or some of them not really visible? And that's it for today's tutorial. I'll hang around if there are any questions, but I think we're out of time. We're slightly over time anyway.